Thank you. Can you hear me? Yeah? Thank you very much. So indeed, I'm going to talk about hot and warm dust in the formal-out planetary system. This is a study that has been done by Jérémy Le Breton, and the paper just came out in AstroPH this morning, so you may want to have a look. So this is again this picture of the formal-out debris. So it has wonderful thin ring at 140 AU, which is seen with the HST here, plus ALMA in yellow. It has a planet, which is real. I'm just quoting Paul Callas. And it has something else that, and Keitsu talked about it, it has some hot and warm dust in the innermost regions, which I call exozodiacal dust here. Okay, so this dust is well known for almost 10 years now, thanks to the Spitzer MIPS images published by Karl Stapelfeld. So you see this glow here, which is due to some excess on the star, which is unresolved. And it has been observed as well with Herschel at 70 microns. You see again a blob here, unresolved excess on the star. And even ALMA actually is detecting something consistent with some excess at the position of the star. But it's unresolved. So what you can say is that there is some excess, it's hot or warm, but it's within 20 AU. You don't know anything about the spatial distribution of this dust. Unless you use spectroscopy and get the temperature of this excess. This is what Kate has been talking about. This is about 170 Kelvin. So this puts this material between typically 10 and 15 AU. So this is what you get without any special constraint. So if you want to have special constraint about the location of the dust, then you need to resolve it. And with current instrumentation, you can only use near-infrared and mid-infrared interferometry to do that job. So we have been using in this study two interferometers, the VLTI first, and the Keck-Müller. Here is what you get when you combine the light of different telescopes with the VLTI. You get visibilities as a function of baseline. I'm not going to explain this plot, but basically at short baseline, an excess emission translates into a deficit of visibility that you can measure, and which gives you a flux ratio between the disk and the star. With the Keck-Müller, it's a little bit different because it's a Müller, so it has very complex transmission map on the sky. So the star is cancelled out. The disk is also a little bit cancelled out. But anyway, we detect an excess null, which is probably an underestimation of the true excess. And it has an interesting feature is that there is some spectral information here between typically 8 and 12 microns. So I'm going ahead. If you really want to understand how interferometry works and how you detect faint exozodiacal dust with these facilities, please discuss with Steve Hertel and Denis Defrère and see their posters to know more about that. So you can summarize all this complex data into basically two information for each instrument, a field of view and an excess. So for the VLTI, we know that what we detect is coming within 3 AU's radius, so a field of view of 6 AU. We know that it's within this field of view that we detect, okay? And the excess is really tiny. It's less than 1% of the flux of the star at that wavelength, K band. Almost the same in the N band. We know that it's coming from a field of view of 4 AU, so it's really confined. And there is a null excess. Again, it's probably an underestimation of this true excess, which is about this value, right? So this is published in 2 papers. So the first thing you may want to do when you have these measurements is to take the zodiacal dust model, our own solar system zodiacal dust model, and to scale it up or down to know, to know how many zodis you need. We call this a zodi. So luminosity of the solar system zodiacal disk. You want to scale it up to know how many zodis you need to actually reproduce this excess here. Sorry, I'm confusing the buttons here. So for the VLTI, you need approximately 5,000 zodis to be able to reproduce this excess. While if you want to do the same match to the n-band excess, then you need 250 ZODs, basically. So these two numbers are obviously inconsistent with each other. What this means is that the spectral energy distribution of the zodiacal dust that we detect around Fomalhaut is different, is probably hotter than the dust around the sun. Okay, so you want to refine a little bit your model to be able to reproduce these observations. So we use a single dust population. We used to do that for previous detection of exozodiacal dust around Vega. This is a paper by Absil et al. 2006 and De Frère et al. Independent detection 2011. And Toseti, which is solar type stars. There was a question about solar type stars with excesses, so Toseti is one. So we use our own model. It's called Greater. It's a radiative transfer model for the debris disk. It's relatively simple because it's optically thin. It's a parametric model, but it comes with very useful features in the context of exozodiacal dust. First of all, it is able to handle mixtures of silicates and carbonaceous material, which is quite important here because carbonaceous material sublimates at much higher temperatures than silicates, so you can get dust much closer to the star. It is able to calculate correctly the size-dependent sublimation distance. The big guys sublimate much closer to the star than the small dust. And since it is quite efficient code, so you can calculate a lot of models, and so you need to do some statistical analysis, Bayesian analysis. This is implemented as well. Okay, here's what you get when you only consider one population. So you have the SED at the top and the Kin null as a function of wavelengths at the bottom. This is a star, stellar spectrum. This is a Vinci data point, translated here in terms of flux. So you see how tiny it is. And we try to fit everything together at first. So these are the red curves here. So you see the SED is more or less properly reproduced. So we slightly underestimate the Vinci detection, but it's consistent with the 10-micron photometry. And if you look at the Kin null, it's quite interesting. So the Kin null are correctly predicted and reproduced at short wavelengths, but when you go to larger wavelengths, it drops and it is not correctly reproduced. And actually, this shape here, this observed shape, so the Kin null that drops first and then which are raising, it's actually very constraining for the model, and it's impossible actually to fit everything together with one single dust population. So what we did, because this model was not able yet to handle two dust populations, we fitted separately the short and the long wavelengths data. So we fitted this VLTI data point and the null values at wavelengths smaller than 10 microns. So no surprise, we fit the CD and the null, but not everything at large wavelengths. And vice versa, if we fit the 10 micron to 12 micron Kin null and the photometry at 10 microns, then we strongly underestimate, these are the green curves, we strongly underestimate the flux at 2.2 microns. So clearly, what this exercise tells us is that we need two dust population to actually reproduce everything. That's one first clear conclusion. And the second thing I didn't tell is that you need to put your grains very close to the star, very close to the sublimation radius, to be able to reproduce this excess here. And this motivated us, actually, this was a good excuse to refine a little bit the sublimation model in our code. And here is how we proceeded. If you consider a grain which has a certain size, which has a certain sublimation temperature, it takes a certain time to sublimate, right? The big guys will sublimate in a much longer time than the small dust particles. So you can actually represent this three-parameter problem in a plot. You have the sublimation temperature as a function of the grain size. You have the astrosilicates here, but I will mostly focus on the carbonaceous material, which is more interesting in the context of the really hot exozodiacal dust. And depending on how long it can survive, then the sublimation temperatures that you need to sublimate everything in this time very much depend on the grain size and the time, of course. So obviously, if you take a big grains, you need a much higher temperature than a small grain. Okay, but the problem is that the sublimation close to the star is not the only physical process that is important. There are other processes like in a classical debris disk that you need to consider before going further. There are competing processes to remove the dust. Collision is one. Pointed Robertson drag is another one. And radiation pressure if the grains are really tiny, so they are removed from the system. So that's what we did for formalot. We consider the removal time scales as a function of grain size. Again, I will focus only on the carbonaceous material here. Here, this sharp transition here is due to the blowout size. Below this size, grains are unbound, and the time scale, their survival time scale is really small, less than 10 to the minus 2 years in the case of formalot. And beyond, you are dominated, in the particular case of formalot, you are dominated by the collision here. So you have the time scale for the grains. So this is the time scale for how long they can survive before they are sublimated, right? So if you combine everything together, you have a sublimation temperature which depends on the grain size. So you use, generally people assume that whatever the size, the sublimation temperature for the astrosilicates is 1,500 Kelvin and almost 2,000 Kelvin for the carbonaceous material. But this is not anymore the case here. The sublimation temperature depends on the grain size, which means that the size-dependent sublimation temperature is even more complicated than before. So you have the sublimation distance here in AU around formalot as a function of the grain size. So you see, obviously, the small grains sublimate at much larger distances because they are hotter, and at smaller distances when they are much bigger. Okay, so we plugged everything into our code, and we tried to fit the VLTI data and the Kin Keck-Nuller interferometric data. And with the additional features that we now include 2 belts instead of 1. And here is what you get. So you have the SCD here. So this is the total flux, the star plus the excess, and this is the excess here in blue. And on the right, you have Kin-Null excess spectrum. This is only one example, but there are more examples of this of such null which are fitted in the paper. And it's okay. We fit approximately everything. So this is the VLTI excess, which is slightly perhaps underestimated, but is more or less reproduced. So the flux is consistent with the 10 micron photometry, and we now reproduce the shape of the null excess curve as a function of wavelengths. In terms of parameters, so we have 2 rings. One ring, we call it hot ring. Maybe Kate would call it very hot ring. And this is our warm belt, which you would call probably hot belt. Okay. We probably need to agree on some definition at some point. Okay, anyway, so this is my hot ring and my warm belt. What we find is that this hot ring is just in the sublimation zone around this star, so less than a fraction of AU. It is essentially made of carbonaceous material and extremely small grains, unbound grains. I will come back to that point later on. The composition of the warm belt is not very much constrained. It can be any mixture of silicates and carbonaceous material. But the grains are much bigger, so they are consistent with being bound. And it's typically located at 2 AU. So we have a belt at 2 AU and something which is next to the sublimation distance. And these are the masses. All right? So the hot ring is much less massive than the warm belt, but it's much brighter, despite the smaller mass. Okay. If you want to visualize which grains are contributing to the total emission as a function of distance, you can make this kind of plot. This is the grain size along the y-axis. This is the distance to the star. So the warm, bound dust grains at 2 AU are basically here. And the unbound grains are basically located here. So you see the sublimation distance here for the carbonaceous material, which is overlaid on this plot. Right. Okay, so now let's try to explain what we see. To make it short, it's impossible actually to assume there is an asteroid belt either at 2AU or even inside, which is in steady state collisional evolution, because the maximum luminosity that you can get is at the edge of the star is 4 to 6 order of magnitude much too low compared to what we observe. So it does not work. So there is another process which is carrying the dust in the regions that we observe. So we need to replenish these belts. So let's start with a warm belt. What we need in terms of mass rate is typically 10 to the minus 9 Earth masses per year. So if you now consider that some material could actually drift inward due to a Poynting-Robertson drag, the mass rate that you get is typically 10 to the minus 12 at most. So clearly you will never be able to actually replenish this belt with this mechanism from this cold belt. You may want to consider another process, which is planetesimal scattering by chains of planets. This was studied by Bonsor et al. In a recent paper. So you need very complex and many planets to actually scatter sufficient material in the innermost region, and even in that case, the maximum mass rate that you can derive is a few 10 to the minus 11, so it does not work. So we don't know. So let's move on and let's continue with the hot carbon-rich belt in the sublimation zone. See, in terms of mass rate, we need typically 10 to the minus 7. Okay, Earth masses per year. So if you assume now that the 2AU belt is replenishing this zone, we need 10 to the minus 11. And I'm not commenting on this one. Basically, we don't have any mechanism to explain that easily, except if you assume that we are discussing about sublimation. So sublimation is producing gas, obviously. And if there is sufficient gas, 10 to the minus 3 Earth masses, then you could actually confine your dust for a sufficiently long time to actually allow this removal process, the radiation pressure, to be compensated by Poynting-Robertson drag. But you need this mass of gas. So I need to go much quicker. I'm sorry. If you want to know more about that, please, for instance, discuss with Amy Bonsor about uncertainty. Just to mention that, okay, so formaldehyde B has a very weird eccentricity, very large eccentricity, very weird orbit, perhaps E equal 0.8, perhaps even higher. We are finding even higher eccentricity for this planet, 0.94, which means that the barycenter is located at 7 to 10 AU, okay, with large uncertainties, but still. So something weird is happening in the inner region of the system. Okay, so you won't know if other stars do have exosodies, but they do. And it does not depend on age. But if you want to know more, just ask. These are my conclusions.
Great. Questions? In the back there.
Maybe you addressed this already, but I'm a little bit confused as to why the hot innermost disk is carbonaceous, whereas the next warmest belt is carbon plus silicon, because I just thought that carbon had a lower sublimation temperature than silicon did. So I would think that the carbon-rich material would be further out in the disk.
That's the other way around. The carbonaceous material sublimate at much higher temperatures than the silicates.
Okay.
So the typical temperature for sublimating the carbonaceous material is typically 2000 Kelvin, and typically 1500 Kelvin for the astrosilicates.
So the carbonaceous material is definitely not a graphite analog, which would have a sublimation temperature of 800 K?
You're right, yeah. Probably, indeed, yeah.
Chris?
Thank you. For the sake of argument, let's forget the mass estimates and the mass delivery rates. If you take a model that could explain the optical depth that is necessary to explain the warm belt and extend that optical depth all the way out to the outer disk, is that inconsistent with observations?
I didn't do that exercise. The only thing that I can show you is this is the surface density that we infer. We do not well constrain this slope here. We know that we need a mass, we need some dust at typically 2 AU. And it has some special extension. It is distributed at large distances, but we don't know exactly what is the slope of the surface density here.
So is it fair to say that the gaps, what we have been referring to as gaps in these disks, may not be gaps, and that there could be dust all the way out to the outer belt?
I appreciate your point, but I cannot answer. I'm sorry. Yeah.
Yeah, one more.
Yeah, so following up from that first question, I don't really understand what's going on with the sublimation rates that you're talking about, because rather than sublimation rate, you have an erosion rate as a function of temperature. And so naming a particular sublimation temperature means you're talking about a particular time scale. So are you modeling sublimation as being a dynamic process, or are you picking a particular erosion time scale for which you compute your sublimation temperatures?
It's not dynamically calculated. So we assume a certain time scale, which is set by the removal processes, either radiation pressure, collisions, and that sets the sublimation time, basically. Assuming, yeah.
And that's where your 2000 Kelvin comes from.
Yeah.
Okay, let's move on. Thank Jean-Charles again.